Welcome back to the deep dive. Today I want to start with a number that, frankly, I found absolutely terrifying when I was reading through Marie Chapter 3 last night. The number is 10 to the power of -6.
Ah, yes. The sterility assurance level. That's a foundational concept in all of this.
It really is. It sounds like a math problem, but it's actually a probability. It means that when a surgeon holds what we call a sterile scalpel in their hand, there is still a 1 in a million chance that a single viable microorganism is alive on that blade. We don't really deal in absolutes in medicine, do we? It's always probabilities.
We really don't. And that specific number, that 1 in a million probability, is the international line in the sand. It's the difference between, say, a successful hip replacement and a catastrophic post-operative infection that literally eats away at the bone. So today isn't just about, cleaning. It's about the invisible war we fight to keep that probability as low as humanly possible.
It's a war of attrition. We're looking at Murray's Medical Microbiology, Chapter 3, and we're also pulling in some key diagnostic principles from Jawet's Chapter 47. Our goal today is to really deconstruct this triad: sterilization, disinfection, and antisepsis. But I want to get beyond just memorizing definitions. I want to understand the physics of how we destroy life on a microscopic scale.
Which is a darker topic than people often realize. We are essentially talking about chemical warfare and thermal destruction. It's directed at pathogens rather than people. The core tension, the conflict that really drives this whole chapter is collateral damage.
That's the perfect way to frame it. That's our mission for this deep dive. How do you nuke the enemy without nuking the host? Because, as Murray points out, you can very easily kill a bacterium with fire.
But you can't set the patient on fire.
Ideally not, no.
Ideally not. So, we have to find these biochemical backdoors. We have to exploit the very subtle differences between human cells and microbial cells. We need to understand why a virus falls apart with a little bit of soap. But a bacterial spore can survive boiling water for hours on end.
Okay, so let's start with those rules of engagement, the hierarchy. I think a lot of people, myself included before this, use these terms interchangeably: cleaning, disinfecting, sterilizing. In my kitchen, they pretty much mean the same thing. But in a hospital, those distinctions are legally binding, aren't they?
They absolutely are. And Murray, in box 3.1, breaks this down into a very strict hierarchy. I think the best way to think about it is like security clearance levels. At the very top, the highest clearance, the most extreme measure you can take, you have sterilization.
The nuclear option.
Exactly. Total destruction. By definition, sterilization is the complete elimination of all microbial life. But when we say all, we aren't grading on a curve here. It includes vegetative bacteria, viruses, fungi, and the ultimate benchmark, the one that really matters, the bacterial spore.
Okay, I want to pin a flag in that concept, the spore. Because it seems to be the final boss in this whole scenario. If something is labeled sterile, that means the spore is dead.
That is the definition.
Correct.
If the process, whatever it is, cannot kill a bacterial spore, specifically from the Bacillus or Clostridium genera, it is, by definition, not sterilization. It represents a truly binary state. You can't be a little bit sterile. You are either sterile or you are contaminated. There's no in between.
Okay, which brings us down to tier 2. Disinfection.
Disinfection is, let's call it crowd control. It destroys the vast majority of pathogens. It'll kill the things that are most likely to get you sick, the vegetative bacteria, the flea viruses, but it leaves the tank standing. It might not kill all the spores. It might struggle with certain non-enveloped viruses. It's a significant reduction, but it's not total annihilation.
And there's a really critical distinction here about where we use these things. You would never disinfect a patient, right?
Never. That is a crucial rule. Disinfectants are for inanimate objects. Floors, benchtops, endoscopes. These are chemicals like high-concentration glutaraldehyde or bleach. If you put those on living tissue, you're causing chemical burns. You're destroying the patient's cells right along with the microbes.
And that's where the third tier comes in, antisepsis.
Yes, the bodyguard. Antisepsis is the application of chemical agents to living tissue to inhibit or reduce the number of microbes. And notice the shift in the language there. We're not promising total destruction anymore. We're promising reduction and, crucially, safety. We accept a lower kill rate because we have to keep the patient's skin intact.
So, to put it all together, if I'm a surgeon scrubbing in for a procedure, I'm practicing antisepsis on my hands. If my team is cleaning the scalpel, that's sterilization. If someone is mopping the floor of the OR after the surgery, that's disinfection.
Precisely. You've got it. And the reason we need these different tiers is because the enemy isn't uniform. The microbes themselves have a hierarchy of resistance.
Right. Let's visualize this. The pyramid of resistance. The source material lays out a clear enemy roster. So who is sitting at the very top of that pyramid just laughing at our alcohol wipes?
Well, technically, prions are at the absolute peak, but they're a special case. They're just misfolded proteins. So in terms of the standard microbiology we fight every single day, it's the bacterial spore, bacillus, clostridium. These are, biologically speaking, the hardest things to destroy.
What makes a spore so ridiculously tough? Is it just a thick shell?
It's so much more than a shell. It's a state of being. A spore is a dehydrated dormant fortress. It has a thick protein coat, yes, but inside that it has a cortex containing a chemical called calcium dipicolinate. This chemical complexes with water, removes it from the core, and basically locks the DNA in place, protecting it from heat and radiation.
And because it's dormant.
It has no metabolism. This is the key. So many of our poisons work by hijacking active metabolic pathways. They trick the cell into eating something toxic, or they block a process it needs to live. You can't poison something that isn't eating or breathing. It's just in suspended animation, waiting for the apocalypse to end so it can germinate again.
So the spore is the ultimate benchmark. If you can kill the spore, you have effectively killed everything else below it on that pyramid.
Exactly. That's why it's the gold standard for verifying sterilization.
Okay, moving down the pyramid. Just below the spores, Murray lists the mycobacteria. Tuberculosis is the classic example.
Ah, yes, the guy in the waxy raincoat.
Explain that analogy. That's a good one.
Mycobacteria have a cell wall that's incredibly high in mycolic acids. It's a lipid-rich, waxy substance, so it's hydrophobic. If you try to use a water-based disinfectant, an aqueous one, it just beads up and rolls right off. It's like trying to wash a greasy frying pan with just cold water. It just doesn't penetrate that waxy layer.
So you need something that can dissolve or cut through that grease.
You need specific agents, like phenolics, which we'll get to later. They are particularly good at disrupting that lipid-rich structure.
Then we have the viruses, and this is where I think a lot of people get tripped up. You have non-enveloped viruses and enveloped viruses. Intuitively, I would think an enveloped virus is tougher.
It has armor, right? An envelope sounds like protection.
It sounds like it should be, but it's actually the opposite. This is one of the great ironies of virology. The enveloped viruses, things like influenza, coronavirus, HIV, they are the wimps of the microbial world.
Why? What is that envelope made of?
It's made of lipids. It's basically a stolen piece of the host cell's membrane. Think of it as a fat bubble. And what happens to a fat bubble when you expose it to soap or alcohol or any kind of detergent?
It just dissolves. It pops.
It pops. And for these viruses, the attachment proteins, the keys they use to get into your cells, are embedded in that envelope. If you dissolve the lipid envelope, the keys just fall off. The virus is neutralized instantly. It's structurally compromised. So the naked viruses, the ones without the envelope, like polio or norovirus, the cause of that awful stomach flu, they're actually the tougher ones.
Much tougher. Their genetic material is protected by a tight, rigid protein shell called a capsid. There's no lipid layer to dissolve. Alcohol often just bounces right off of them. You need stronger chemistry, like bleach, an oxidizing agent, to actually break apart that protein shell.
That is such a crucial mental model. Spores at the very top, then mycobacteria, then the naked, non-enveloped viruses, and way down at the bottom are the easy targets. Fungi, vegetative bacteria, and the wimpy enveloped viruses.
Correct. So you can see how choosing your weapon depends entirely on knowing your enemy.
Okay, we know the enemy. We have our target list. Let's open the weapons locker. We're moving into section 2 of our deep dive. Sterilization, total destruction. And the oldest weapon is still the king. Heat.
But not just any heat. It has to be moist heat.
The autoclave. The source material calls this the gold standard. 121 degrees Celsius, 15 psi, 15 minutes.
Those are the coordinates for microbial death. Those numbers are on every exam.
Why those specific numbers? Specifically, why the pressure? I mean, water boils at 100 degrees Celsius. That feels pretty hot to me. Why isn't just boiling something enough to sterilize it?
Boiling is great for killing vegetative bacteria, your E. coli, your staph. But remember that calcium dipicolinate fortress inside the spore. It stabilizes the DNA so well that a spore can survive boiling water for hours. To denature that reinforced protein structure, you have to push the thermal energy way higher. You have to hit 121 degrees.
And you can't get liquid water to 121 degrees in an open pot on the stove. It just turns to steam and leaves at 100 degrees.
Exactly. Basic physics dictates that at sea level, water boils at 100. The only way to get steam hotter is to increase the pressure. That 15 psi pounds per square inch above atmospheric pressure clamps down on the molecules and forces the temperature up to that magic 121 number.
Murray makes a really interesting point about the latent heat of condensation here. This is why steam is so much more effective than dry, hot air, right?
Yes, this is pure thermodynamics. When that 121-degree steam hits a cold surgical instrument, it instantly condenses back into water. That phase change from gas to liquid releases a massive amount of energy, the latent heat, directly onto the steel surface. It transfers heat much, much faster and more efficiently than dry hot air ever could.
It's the difference between putting your hand in a 100-degree oven for a few seconds versus putting your hand in 100-degree boiling water.
One is uncomfortable, the other destroys your skin instantly. That's why dry heat sterilization is so inefficient. It requires something like 160 degrees Celsius for 2 hours, whereas the autoclave gets the job done in 50 minutes at 121.
But not everything can handle that kind of pressure cooker environment. I mean, we use so much plastic in modern medicine, fiber optics, electronics. If I throw a colonoscope in an autoclave, I'm going to have a very expensive melted paperweight.
You are. So for all the delicate stuff, the heat-sensitive items, we need what's called cold sterilization. And historically, the heavy hitter in this category has been ethylene oxide gas, or ETO.
ETO, this stuff sounds rigorous.
It's a colorless gas. It's odorless until the concentration gets very high, which is dangerous. And its mechanism is alkylation. It's an alkylating agent.
Let's unpack alkylation. We see this word a lot in chemotherapy drugs as well. What is it actually doing to the microbe on a molecular level?
Imagine the DNA double helix, or a critical enzyme. They rely on specific hydrogen bonds and functional groups, like hydroxyl or amino groups, to hold their shape and do their job. An alkylating agent like ETO comes in and forcibly attaches a carbon chain, an alkyl group, to those molecules. It's like pouring superglue into the gears of a tiny watch. The DNA can't unzip to replicate. The enzymes freeze up. The cell dies.
That sounds incredibly effective, but if it does that to a bacterium, surely it does that to our cells too.
Oh, absolutely. ETO is a triple threat. It's carcinogenic, it's mutagenic, and it's also flammable and explosive. It is nasty stuff to work with.
And there's a specific logistical nightmare with ETO that Murray points out regarding aeration.
Yes. Because it's a gas, it soaks into porous materials like plastic tubing or rubber. If you sterilize a breathing tube with ETO and then immediately hook it up to a patient in an ICU, that residual gas will leach out and chemically burn the patient's trachea and lungs.
So you have to let it sit and breathe, basically.
For a long, long time. The aeration cycle is typically 12 to 16 hours. It's a massive bottleneck in the hospital workflow for reprocessing equipment.
Okay, so is there a better way, something that feels a bit more 21st century than this toxic, explosive gas?
There is, thankfully, hydrogen peroxide vapor, which is often used with plasma gas technology.
Plasma always sounds like something out of science fiction.
It basically is. What you do is you vaporize a concentrated solution of hydrogen peroxide, H2O222, and then you blast that vapor with microwave or radio frequency energy. This excites the molecules into a plasma state, a fourth state of matter, which creates a cloud of highly reactive free radicals.
Chemical bullet.
The perfect term for them. These highly reactive hydroxyl radicals just tear apart anything they touch. Microbial cell walls, DNA, proteins. But the magic trick is what happens when you turn the machine off. The plasma collapses back down into harmless water vapor and oxygen.
So there's no toxic residue to worry about.
None whatsoever. There's no need for a long aeration time. You can use the instrument almost immediately. It's far safer for the staff and for the patient. It has largely replaced ETO for many applications. Its main weakness, though, is that it struggles with really long, narrow, lumens-like long tubes, where the plasma can't fully penetrate deep inside.
So we've covered heat and we've covered gas. What about liquid chemicals? Can you sterilize something just by soaking it in a tub?
You can, but it's tricky and time-consuming. There are two main players here that you need to know: peracetic acid and glutaraldehyde.
Glutaraldehyde. I feel like I can smell this word. It has that sharp hospital smell.
It has a very pungent, irritating odor. Glutaraldehyde is interesting because it's what I'd call a double agent.
How so? What do you mean by that?
It all depends on how long you soak the item. If you soak an instrument in a 2% glutaraldehyde solution for about 20 to 45 minutes, it acts as a high-level disinfectant. It kills almost everything, but maybe not all of the really tough spores. But if you leave that same instrument soaking for 10 hours...
It crosses the line into full sterilization.
Exactly. It eventually kills all the spores. But as you can imagine, nobody likes leaving a surgical suite or an endoscope inactive for 10 hours. Plus, glutaraldehyde is toxic to handle. It's a known cause of asthma and skin sensitization in hospital staff.
So we're moving away from it where we can.
Yes. Peracetic acid is becoming more popular. It's another oxidizer, similar in mechanism to hydrogen peroxide. And its breakdown products are much safer. It just breaks down into acetic acid, which is basically vinegar and oxygen.
Before we leave sterilization, I have to ask, how do we know it worked? I mean, you open the autoclave, the steam comes out, the tools look clean, but you can't see a 1 in a million spore.
You have to trust, but verify. And we verify using biological indicators, the classic canary in the coal mine.
And what is that, canary?
It's a species called Bacillus styrothermophilus.
Okay, break that name down for me.
Styrothermophilus. Thermophilus means heat-loving. These bacteria naturally live in hot springs and geothermal vents. Their spores are evolutionarily designed to survive extreme heat. They are tougher than anthrax spores, tougher than tetanus spores.
So the logic is, if the autoclave cycle killed this heat-loving superspore, then it definitely killed any of the wimpy pathogens that might have been on the instruments.
That's the logic exactly. You put a little vial containing these spores in the center of the autoclave load, the hardest place for the steam to reach. After the cycle, you take it out and try to culture the spores in the lab. If they don't grow, the load is certified sterile. If they do grow, you have a big problem.
You have to recall and re-sterilize everything. That is such a clever, elegant system.
It's the only way to be truly sure you've achieved that 1 in a million standard.
Let's move down the hierarchy now to Section 3, disinfection. Murray calls this the sliding scale. This is where we get into the Spalding classification system.
Yes. Earl Spalding developed this system back in the 60s, and it's still the foundation of how we think about this. He mapped the risk of infection to the method of cleaning. He divided all medical devices into 3 categories: critical, semi-critical, and non-critical.
Okay, so critical items are things that enter sterile tissue. The bloodstream, bone, the abdominal cavity, those must be sterile. We just covered that. Scalpels, needles, implants.
Right. The next level down is semi-critical. These are items that touch intact mucous membranes but don't typically penetrate the body. Think endoscopes, laryngoscope blades, vaginal specula.
So a colonoscope going into the colon.
Exactly. A colonoscope enters the colon, which is already full of bacteria. So the device doesn't need to be sterile like a scalpel, but it needs to be very, very clean to avoid introducing a new pathogen. For these, we use high-level disinfection.
And what agents are we using for that?
Often those wet chemicals we just talked about, but for shorter times. Glutaraldehyde for 20 minutes, or peracetic acid. But Murray absolutely screams about one specific rule here, and it's probably the most important point in the whole chapter. You cannot disinfect dirt.
It cannot be overstated. You must meticulously clean the instrument before you disinfect it. You have to scrub off all the visible blood, the mucus, the feces, the organic matter.
Why? Why can't the glutaraldehyde just blast through a speck of blood?
Because that organic matter physically shields the microbes and chemically inactivates the disinfectant. Think about chlorine, bleach. It reacts with protein. If you have a glob of dried blood on an instrument, the chlorine molecules will sacrifice themselves, attacking the blood proteins on the surface. They get used up. By the time they could penetrate to the bottom of that glob where the bacteria are hiding, the chemical is inert.
So you're just disinfecting the top layer of the blood clot, effectively.
Exactly. And you're shielding the bacteria underneath. This is where most failures in infection control happen. It's not that the chemical was wrong. It's the failure to clean first.
Okay, let's drop down another level. Intermediate level disinfection.
This is for surfaces or items that might touch intact skin or have accidental contact with bodily fluids. The key litmus test here, the bug we measure it against, is Mycobacterium tuberculosis.
Why TB?
Because, as we talked about with the pyramid, TB is the hardest non-spore-forming bacteria to kill because of that waxy cell wall. So if a disinfectant is proven to be strong enough to kill TB, we classify it as intermediate. This category covers your alcohols, your iodophores, and your phenolics.
And finally, the bottom of the barrel. Low-level disinfection.
This is the bottom shelf. This is your quaternary ammonium compounds, or quats. These are your standard hospital cleaning wipes for bed rails, blood pressure cuffs, stethoscopes, things that only touch intact skin.
And what do they kill?
The easy stuff. Vegetative bacteria and the enveloped viruses. They do not kill TB, and they definitely, absolutely do not kill spores.
And this leads us to a specific horror story that Murray highlights. The hospital superbug connection with Pseudomonas.
Pseudomonas aeruginosa. I call it the cockroach of the bacterial world. It's a gram-negative organism that loves moisture and can survive on almost nothing.
You called it a cockroach. Why?
Because it survives almost anything we throw at it. There have been documented hospital outbreaks where they're using quaternary ammonium disinfectants to clean surfaces in, say, a burn unit, and they kept finding Pseudomonas spreading from patient to patient.
It was resistant to the quads. It was worse than resistant. They investigated and found that the Pseudomonas was living inside the bottle of disinfectant. It was actually using the carbon molecules in the cleaner as a food source.
He was eating the poison.
It was eating the poison and thriving. So the nurses were going around wiping down tables and equipment thinking they were sanitizing. But what they were actually doing was painting a pure, concentrated culture of Pseudomonas onto every single surface.
That is absolutely horrifying. It's like trying to put out a fire with gasoline. It effectively is. And this is why, for high-risk areas or during an outbreak, you cannot rely on low-level quats. You have to escalate to something much stronger, like a chlorine-based cleaner, a bleach solution.
Which brings us to another really stubborn bug. C. diff. Clostridioides difficile. It causes that terrible, sometimes fatal colitis.
Right. And what's the key feature of C. diff?
It's a spore former.
It's a spore former. So think back to our pyramid. Where are spores?
Right at the top. Hardest to kill.
And what's the most common thing we use for hand hygiene in hospitals?
Alcohol-based hand sanitizer.
And where is alcohol on the weapon list?
Intermediate level. It doesn't kill spores.
Exactly. So if you walk out of a C. diff patient's room and you just use the alcohol hand sanitizer on the wall,
I've done absolutely nothing to the spores.
you've done nothing. You've essentially just given the spores a nice alcohol bath and spread them around your palms. The alcohol does not kill them. That is why, for C. diff, the protocol is strict. You must use soap and warm water.
Because you're relying on the mechanical friction and the surfactant action of the soap to physically wash the spores off your hands and down the drain.
Physical removal is the only option when chemical destruction fails. It's a critical point.
Let's pivot now to Section 4, Antisepsis. We're moving from inanimate objects like floors and tools to living human skin.
The goal here shifts completely. We aren't trying to sterilize a patient's skin that would require boiling them or setting them on fire. We're trying to reduce the bioburden, the number of microbes, enough to prevent an infection during a procedure like surgery or inserting an IV line.
The MVP in this category, the most commonly used agent, is alcohol, isopropyl or ethyl. But there's a really counterintuitive fact that always catches students out on exams. You go to the pharmacy, you see 70% alcohol, and you see 90% or 99% alcohol. Logic says the higher concentration must be stronger.
But logic is wrong in this case. In microbiology, 70% alcohol is superior to 100% alcohol as an antiseptic.
Unpack that for me. Why is diluting it with water better?
It comes down to the mechanism of action. Alcohol kills by denaturing proteins. It causes them to unfold and lose their shape. But to do that efficiently, you need water molecules to participate in the chemical reaction. Water also helps the alcohol to penetrate the bacterial cell wall in the first place.
So what happens if you use pure 100% alcohol?
It acts too quickly and too harshly on the outside of the cell. It severely dehydrates the cell wall, causing the proteins on the surface to coagulate instantly. This creates a hard, impermeable crust around the bacterium. It seals the bacteria up, it seals it. The inside of the cell might actually go dormant and survive. You've effectively preserved the germ rather than killed it. You need that 30% water to slow down the process and allow the alcohol to get inside and do its work properly.
That is wild. The water is actually the delivery vehicle for the poison. Now, alcohol has one major flaw as an antiseptic. It has no residual activity.
Right. It works great for a minute, but then it evaporates. And once it's dry, it is done working. 10 minutes later, bacteria from deeper in your hair follicles can migrate back onto the skin surface.
So for something like a long surgery or a central line that needs to stay in a patient's neck for days, we need something that sticks around.
And for that, we have chlorhexidine.
The long game.
Exactly. Chlorhexidine is a cationic molecule, which means it's positively charged. Skin, on the other hand, is generally anionic or negatively charged. So it binds electrostatically to the top layer of the skin, the stratum corneum.
It's like a chemical magnet sticking to the skin.
Yes, and it stays there and keeps killing bacteria for hours, even days after you've applied it. That's why it's the standard of care for pre-surgical scrubs and for maintaining central lines. It's a marathon runner, whereas alcohol is just a sprinter.
What about iodoforce? Betadine. That classic orange-brown paint we see in movies before a surgery.
Iodophores are interesting. Elemental iodine is a fantastic, powerful killer. It's an oxidizer. But pure iodine is very harsh. It burns the skin and causes a lot of allergic reactions. So what we do is we complex it with a carrier molecule, usually something called povidone.
A carrier.
Think of povidone as a cage. It holds onto the iodine and releases it slowly over time. This dramatically reduces the irritation and toxicity, but maintains the killing power. It's very broad spectrum, but like alcohol, it tends to get inactivated by blood and serum more quickly than chlorhexidine does.
And just quickly, triclosan, I feel like I see this listed as an ingredient in toothpaste or deodorant soaps.
You do. It's a phenolic derivative. It's really more of a consumer product. It's a bacteriostatic agent, meaning it stops bacteria from growing, but it's pretty weak against viruses and fungi. It's not a serious hospital-grade antiseptic.
Okay, we've covered the hierarchy of control. We've covered the weapons. Let's get nerdy with Section 5. Mechanisms of action. How do these things actually kill on a molecular level? Murray groups them into 4 main modes of attack.
Right. Let's simplify the molecular violence.
Mechanism 1, denaturation. This is the brute force method. This is heat.
Think of a protein as a very complex piece of origami. It's folded into a specific, unique 3D shape to do a specific job. Heat just shakes the molecule so violently that all those delicate folds come apart. It becomes a useless, tangled string. And you can't refold it. You can't unboil an egg.
Mechanism 2, alkylation. The superglue.
We talked about this with ethylene oxide and glutaraldehyde. They add carbon chains to the functional groups on DNA and proteins. It's like gumming up the zipper so the DNA cannot replicate, or freezing an enzyme in place so it can't function.
Mechanism 3, oxidation. The chemical bullets.
This is your hydrogen peroxide, your chlorine bleach, your iodine. These agents are electron thieves. They rip electrons off of other molecules, creating free radicals that act like shrapnel inside the cell. They smash through chemical bonds in lipids and DNA. It's chaotic, widespread, and irreparable damage.
And mechanism 4, membrane disruption. The dissolvers.
This is the mechanism for alcohols, phenolics, and the quats. They act like detergents. They are molecules that can insert themselves into the lipid bilayer of the cell membrane and basically pry it apart.
Pop the balloon.
Exactly. All the cell's contents leak out, and it dies. And this directly explains why phenolics are the specific choice for killing TB.
Okay, connect the dots for me there.
TB has that waxy, lipid-rich cell wall, remember? Phenolics are particularly good at disrupting and dissolving lipids. Therefore, phenolics can penetrate the armor of TB much better than other water-based agents can. The mechanism of the weapon perfectly matches the weakness of the target.
It always comes back to the structure of the microbe. Before we hit the quiz, I want to touch on the sterile site concept from Jatz. We usually think about killing germs to prevent a patient from getting an infection. But Jatz makes the point that we also do it to prevent confusion.
Diagnostic confusion. This is a huge, huge deal in clinical medicine. Inside your body, your bloodstream is sterile. Your cerebrospinal fluid is sterile. If you need to draw blood for a culture because you suspect sepsis and you don't clean the skin properly with an antiseptic,
You pick up the normal skin flora, the Staphylococcus epididymis that's just living on the skin.
you push it right through the skin with a needle and inject it directly into the blood culture bottle. 2 days later, the lab calls the doctor and says, hey, there's bacteria growing in your patient's blood.
And the doctor's immediate thought is that the patient has sepsis, a bloodstream infection.
Exactly. So they start powerful, broad-spectrum antibiotics. They keep the patient in the hospital for 3 extra days. They might order an expensive echocardiogram to look for vegetations on the heart valves. And it was all because of a contaminated specimen from a dirty needle stick.
So proper antisepsis isn't just about patient safety in that moment. It's about diagnostic truth.
A contaminated specimen is often worse than no specimen at all. It sends you down a completely wrong and potentially harmful path.
All right, we've unpacked the hierarchy, the weapons, the mechanisms, and the clinical stakes. I think it's time to test the listener's recall.
I love this part. Active recall is the only way to make this information stick.
Okay, I'm going to read a clinical scenario. I'll pause for about 3 seconds. You, the listener, try to answer it in your head. Then our host will reveal the answer and we'll discuss the why. Ready? Question 1. You have a set of surgical instruments. You accidentally set the autoclave to run at 100 degrees Celsius for 30 minutes instead of the required 121 degrees. Will these instruments be sterile?
The answer is an emphatic no.
Why not?
100 degrees Celsius is just the temperature of boiling water. It's great for killing vegetative bacteria, but it does not have enough energy to kill bacterial spores. To be considered sterile, you must kill the spores, and that requires 121 degrees Celsius under 15 psi of pressure.
Question 2. You need to verify that your hospital's autoclave is working correctly. You place a biological indicator vial in the center of the load. Which specific organism spores are inside that vial?
That would be Bacillus stereothermophilus,
Why that specific one?
because it's a thermophile, a heat-loving organism. Its spores are exceptionally resistant to heat. The logic is that if your machine can kill this super-resistant spore, it is guaranteed to have killed any of the less resistant pathogens that might infect humans.
Question 3. A patient in the burn unit develops a severe skin infection. The lab identifies Pseudomonas aeruginosa. The hospital's infection control investigation eventually finds the bacteria growing inside a bottle of disinfectant being used on the ward. Which class of disinfectant was most likely being used?
That has to be quaternary ammonium compounds, or quats.
The cockroach strikes again.
Pseudomonas is notoriously resistant to low-level disinfectants like quats. It can even metabolize them, using them as a carbon source for growth. It is a classic cause of outbreaks related to contaminated disinfectant solutions.
Question 4. You're teaching a new medical student about proper antisepsis before placing an IV. They see a bottle of 70% ethyl alcohol and a bottle of 100% ethyl alcohol and ask why you're using the weaker one. What is the physiological reason?
The presence of water is required for the alcohol to effectively penetrate the bacterial cell.
Can you explain that a little more?
Sure. Water is required to catalyze the denaturation of proteins inside the cell. Pure 100% alcohol dehydrates the outer surface of the bacterium too quickly, creating a coagulated shell that can actually protect the inside of the cell rather than killing it.
Question 5. You are in charge of reprocessing a bronchoscope that was just used on a patient with active tuberculosis. You need an appropriate intermediate-level disinfectant. Which class of chemical is known to be specifically effective against the lipid-rich cell wall of mycobacteria?
That would be the phenolics.
And what's the mechanism there?
Phenolics work by disrupting and dissolving lipid membranes. Since the cell wall of Mycobacterium tuberculosis is composed of a high concentration of lipids mycolic acids, phenolics are particularly good at penetrating that waxy armor where other agents might fail.
Question 6. You need to sterilize a delicate, heat-sensitive plastic heart valve. You choose to use ethylene oxide gas. What is the critical safety step that must be taken after the sterilization cycle is complete, before the device can be implanted in a patient?
You must perform aeration, typically for 12 to 16 hours.
And what's the consequence if you skip this step?
ETO is a toxic alkylating agent. It absorbs into porous materials like plastic. If it's not fully aerated, that residual gas will leach out and cause severe chemical burns to the patient's heart tissue. It is an absolutely critical safety step.
Fantastic. If you nailed those questions, you have a solid grasp of this chapter. If not, go back and review Murray Chapter 3. The tables in that chapter are absolute gold.
They really are. It's worth the time to go through them carefully.
Before we sign off, I want to leave you with a provocative thought. We've spent this entire deep dive talking about how to kill these things. Better chemicals, higher heat, stronger gases. We are, in medicine, obsessed with sterility.
But biology is reactive. Evolution doesn't just stop because we built a hospital.
Exactly. We talked about Pseudomonas literally eating our disinfectant. We talked about C. diff spores that just ignore our alcohol hand sanitizers.
So the question is, by creating these ultra-clean, sterile environments, are we inadvertently training the enemy? Are we running an evolutionary boot camp for superbugs?
Think about it. In a natural environment, like a forest, there are millions of different bacteria competing. Good bacteria often crowd out the bad bacteria. But in a hospital, we wipe out all the wimps. We clear the entire playing field.
And the only things left standing are the absolute tanks, the spore formers, the ones with the waxy coats, the multi-drug-resistant organisms. The cleaner we get, the tougher the survivors become.
It's the paradox of control. The harder you squeeze, the stronger the resistance gets.
It reminds us that effectiveness in this war isn't just about brute force. It's about having the intelligence to match the right weapon to the right enemy in the right setting.
A humbling thought to end on. Master the hierarchy. Understand the weapons.
And for goodness sake, please wash your hands.
See you in the next deep dive.